All right, line A1, learning task 11. We're going to take a look at electrostatic charges, which is going to be a new component for us all over here. And we're going to use them because we need to go and develop all the theory that lies behind what is going to be referred to as our capacitor. And a capacitor is almost like Newton's third law in that it is going to be the opposite to what our inductor does in so many ways. It's going to oppose a change in voltage. We're going to see how it opposes a change in voltage. It's going to go and use current to oppose a change in voltage. And it's going to go and give us a type of power that's going to be opposite to that of an inductor. And so really we're going to be able to go and create this counterbalancing force, which is great because we do need inductance. So we're going to need to have some way to offset that as well. In order to get to that point, we're still quite a ways away from it, we have to start with the idea of an electric field or an electrostatic charge. An electric field is going to be a three-dimensional region. In other words, it exists all the way around something, and it is with the region that an electric charge is acted upon by an electric force. Now, an electric charge is just simply a body, any type of a body that contains either a positive or a negative charge. You've seen this before when you walk across a carpet and you touch a doorknob and you build up that static charge, and it just, you get that little tick as you discharge, or you might have seen it in the form of thunder, where we've got, thunder and lightning, where we have these clouds that are going to go and build static charges and then go and discharge them. Those are all, fairly violent examples of discharging electrostatic fields. What we're going to look at is not so much the discharge as the charging action of those electrostatic fields. And in order to do that, we have to just examine charged bodies. Now, we've got two charged bodies that are shown over here. We have got our positively charged body. We have got our negatively charged body over here. You'll note that they have got opposite arrowheads. The positively charged body is seen as if it had lines of force that were going to go and travel away from that positively charged body. And my negatively charged body is seen as having lines of force that are going to be traveling to that body. All of these lines are always going to start at a straight 90 degrees off of the surface of the electrostatically charged body. They're going to emanate outward, and if there was no other forces in the universe acting on them, they would extend out, into infinity. In all honesty, there are a ton of other charged components, and those other charged components are going to go and bend those lines as those lines move out. They're just going to get acted upon by other components, and that's what we're going to do inside of our capacitors. We are going to go and bend and act upon lines. Like all charges, they do have laws that are going to be very similar to our magnetic laws. They're going to go and have forces of attraction and forces of repulsion. If I take a look at this arrowhead moving out and I take a look at this arrowhead moving in, I know that these lines are going to want to attract each other. So I'm going to go and have a force of attraction between a positively charged body and between a negatively charged body. Also, if I would go and have two positively charged bodies, we'll change this one over here to a positively charged body, it would have arrowhead that would then be going outwards. Ignore those bottom little arrowheads. We'll just take a look at these outwards facing ones. And if I were to go and take these two positively charged bodies, and if I were to go and bring them together, what I would be doing is I would be bringing these electrostatic lines up against each other. And when I do so, they're going to go and give me a force of repulsion. It's like magnets. When you take two north poles of a magnet and you shove those things together, you feel that repulsion that's going to go and happen. If you take a north and a south pole on a magnet and you bring them together, you start to feel that attraction. And you also feel that as you get these things closer, you're going to go and increase the amount of attraction or the amount of repulsion that you're getting off of those, in that case, magnetically charged bodies. In electrostatically charged bodies, we're going to get the same thing. We are going to be able to go and attract or repel based upon what the charges are. We do have what we refer to as charge separators. Charge separators are simply going to be anything that is able to go and take a component that is balanced, and nature tends to want to go and balance. So if I've got a block of any type of substance, it's going to try to maintain as much net neutrality as it can. However, as soon as I go and take a charge separator, that charge separator is able to go and move negatively charged components to one side, positively charged components to the other. Oftentimes these are going to be chemicals, like in a battery. A battery is a charge separator. Other times they can be magnetic forces, like in a generator or something like that. Other times they can be caused by piezoelectric, thermoelectric, any one of our other types of forces that are going to go and separate charges. We refer to them as just being, sources of electricity, but technically speaking, a source of electricity is going to be a charge separator that is going to go and take something that was balanced. We're going to go and have, a nucleus and electrons that are going to be traveling around the outside of that nucleus. It's going to take what we have for a balanced electron, and it's going to go and separate charges. If you go back to your very elementary the physics that you covered at the very beginning of first year, you would have gone through the structure of the atom. And you should be familiar with the fact that every atom has got my electrons around the outside, and it's got my protons and my neutrons that are going to be in the center. The protons and neutrons are going to go and give us this thing mass, kind of like our solar system. The electrons are going to go in orbit around that. Those protons that we have here in the center are going to go and have a positive charge. The electrons are going to go and have a negative charge. And you should be familiar with the concept that every one of my elements is going to go and have a periodic number. That periodic table of elements, you've probably seen it, maybe you remember stuff about it, maybe you don't, but that periodic table of elements is simply going to be a definition of the number of protons that are going to be in the center. And if this thing is a balanced, a non-ionized type of atom, if this thing would have a element, atomic number of 4, that would mean that it would have 4 protons, and in a balanced state, it should have 4 electrons. When I take an outside force and I put that outside force into here, so we'll just we'll draw some squiggly green lines here. We'll say that that represents some sort of a charge separator. What that charge separator is going to try to do is it's going to remove one of my components. So it's going to go and kick one of those things out. At this point, we have got an unbalanced circuit. Nature tends to want to balance. That charge separator has booted this thing out. And let's call it a battery that we have here. It is now going to separate it out like that. And what happens is all of these electrons accumulate on the negative end of the battery. And then they will go and follow any sort of a circuit. If we create a circuit, all that a circuit does is it allows whatever we have charge separated to go and travel, take this incredible journey all the way back home. This electron's going to leave, go through a little bit of resistance, and it's going to go and make its way all the way back over here. That's the principle of charge separation. Now, charge separation is when we actually go and pull an electron off of something. When we go and just distort something, we end up at, a different sort of state. We end up at one that is a state of distortion, where we have not quite done enough to go and rip this thing completely out of the orbital, but we have stretched out that orbital. Those orbitals want to go and balance. Nature tends to want to balance always, and so as soon as we go and stretch something out like that, we are going to go and have forces, elastic forces, that we can go and use to activate other components. We'll examine that all a little bit more in detail later on, but that's the background that we're working from, this whole concept of charge separations that we are going to go and have. We do have a law called Coulombs Law, and Coulombs Law, they have it written out in words. Words are always a little bit harder to understand, and they also have it written out in a formula. Coulombs Law states that the electric force between 2 point electric charges is directly proportional to the product of the 2 charges and inversely proportional to the square of the spacing between them. Written out, we get this formula. F, that's going to be the force of attraction or repulsion, is measured in newtons, is equal to K. That's going to be the constant of proportionality. In other words, the type of material that I'm going to go and have between the 2 charges. K multiplied by, I'm going to bracket this whole thing here, Q1 times Q2. So this is the force on number 1 and force on number 2. And they could either be positive or negative. If they're both positive, they would be a force of repulsion. If they're both negative, they would be a force of repulsion. If one's positive and one's negative, it would be a force of attraction. All over top of my distance squared, which is going to be the distance between the charge in meters itself. Coulombs, by the way, are going to be a physical finite quantity of electrons that we are going to go and be looking at. You need to be familiar with what the Coulomb is. You would have covered this back in the beginning of first year. First year, you went over what a Coulomb is. A Coulomb is a definite quantity. It's like having a coffee cup full of electrons, or a measuring cup full, or whatever it is that you want to have full of electrons. We call that a coulomb. What an amp is a measure of the amount of coulombs that are flowing through a system. Basically, if you would take a coffee cup, probably a lot of you have a coffee cup in front of you right now, if you imagine that coffee cup being full whatever you have inside of it is going to go and be your coulombs. How quickly you pour that out is going to go and be your current flow. Current flow is just simply a measure of how quickly we're pushing the coulombs, or the actual finite number of electrons, through the system. So this law that we're seeing over here is talking about static quantities that we are going to go and have. You know, it's a cup of electrons and another cup of electrons over here, and how, you know, close we put them together is going to go and define a charge off them. We're going to come back to this whole idea of coulombs later on, or discrete physical quantities of electrons. We've got another formula that's also given to us inside here, and that one is going to be the E is equal to F over top of Q. And this is going to go and talk about my field intensity. We're going to express our field intensity in newtons per coulomb. And what we're going to go and have is we're going to have F, which is going to be the charge in newtons. This is going to be this F from over here that we're taking down. I shall draw the arrowhead on the other end. It would make more sense like that. So whatever I take, my charge 1, charge 2 over top of the distance and the type of material that's in between them, I'm going to go and create a force in newtons. And then I'm going to go and compare that amount of force that I have compared to the total amount of coulombs that I have. And we're going to see that, you know, if we change what we have in between them, or we change the distance, we're going to go and get, for the same amount of coulombs, pretend this is 1 cup, and this is 1 cup as well. I know we don't measure electrons in that, but we're just working with the visual over here. But this, if this was 1 cup and 1 cup, we're going to get a force that's going to be based upon what the distance is between them and what the type of material is between them. What we do is we can take that force down here and we compare that to what's the amount of force that we have compared to the 2 cups of coulombs that we're using to go and generate that. And we'll see that as we change distances and materials in between, we will be able to go and change the amount of electric field intensity that we are going to have. Once again, this is just kind of base background that we're going to use for these capacitors. Let's take a look at our next slide that we're going to have here. Next illustration that we have shows charged parallel plates. And it shows that we're just creating an electrostatic field anytime that we take a power support source. Over here, we've got a battery, positive and negative. We've got that charge separator inside there that has gone to destroy that equilibrium of my atoms inside there, rip some electrons, push those electrons to the negative plate. I'm just going to go and draw a bunch of electrons over here, and has left holes. Anytime that we remove an electron, we're going to call that a hole. You'll see me drawing throughout the entirety of this module electrons as dots, holes as little circles. For every action, there's an equal and opposite reaction. So for every electron that I take, I'm going to have a hole that's created. I should have an equal number of those. When I take this battery and I apply it to 2 plates over here, and I place those plates like that, what I'm going to see is I'm going to have all these holes. Now, do these holes like each other? Absolutely not. They do not like each other because they've got the same type of charge, right? They've got a net positive charge on them right now. Same with these electrons, are going to have a net negative charge on them right now. And so they're going to distribute because they don't like each other. They're going to try and get as far away from each other as they possibly can, but there are billions of them. So they're just going to spread out across the plate. So I'm going to go and have a net negative charge that's going to be seen across this plate, and I'm going to have a net positive charge that is going to be seen across this plate over here. As a result of that, I am now going to go and have an electrostatic field that is going to be in between here. Basically, anything that I introduce into this electrostatic field is going to be affected by it. We're going to go and take a look at placing some stuff in the middle in a minute, but right now let's just talk about the electrostatic field. If I were to go and take something that has got a positive charge, and if I were to go and move it down into this field, what would happen? Well, we would see that it would be acted on by these positives, be repelled by those positives, and it would be attracted by these negatives over here. And so anything that I would enter into here is going to get attracted over towards that plate. We use this in all sorts of different industrial applications. Industrial air cleaners, or precipitators as they're commonly called, are going to go and use this, where we're going to have a set of charged plates. We're going to make a negative set of charged plates. We'll pass all of our dust through it. It's going to charge all of our dust negatively. And then we'll have a positive set of plates that, whoop, it's just going to go and pull them all over too. Okay, that's not what this is here for. That's just another place where we use this, or another way that we can use these electrostatic fields. What we're going to take a look at right now is going to be this other formula that they're going to go and show us that's a derivative of our, E is equal to F over top of Q. And this new formula is going to be E is equal to my volts over top of my distance. I'm able to go and say that the volts that I'm going to go and have, the field intensity in volts per meter, is equal to the potential difference in volts over top of the distance in the plates separating these. And we're going to measure that distance inside of meters. Now, they do get this E out of this other previous formula that we had that said that E is equal to F over Q. And so all they did is they said, look, we can go and take that F over Q and we can drop that in there and we can say that that's going to be my volts over top of distance. And so they're just dropping those in, moving these formulas around. Don't worry so much about how they've derived the formula. Worry about what the formula itself is actually telling us. It's telling us that, look, if I want to go and see an intensity, a field intensity increase, I can go and increase my value of volts, which would increase my field intensity, or I can go and decrease my distance between the plates, which is going to, decrease my distance, which would also go and increase my field intensity. Either one of these is going to go and create a difference to my field intensity. The more intense the field is, the more intense the way that it is going to react on anything that's going to be placed inside of here. We're going to take a look at placing some stuff inside of this field. First thing we're going to start with placing inside of that field is we're going to place a chunk of conductor. If we were to go and place a chunk of conductor in between, but we would not go and make an actual connection. So once again, we've got that battery. We've got all of those electrons on this side. We've got all of those holes that are going to be on this side over here. We place that battery across two plates. We're going to go and create charges across here. And then if we place a conductor inside here, what happens inside of this conductor is any negatively charged components, electrons, are going to get attracted towards the positives, right? We got all these holes over here that are distributed from my battery, pushed out. The battery is just going to go and take all this extra room. It's like extra real estate. It says, hey, look, I've got all of you holes crowded together on this pole of my battery. Get out there, spread yourselves out. This is annoying that we're all clumped together. Same with these ones over here, all these electrons. Get out of there, spread out across here. So we've got all these holes, all these electrons. Because we've got all of these holes here, we've got this positive charge. And so inside of here, what happens is that what before would have been a completely neutral chunk of conductor, all of a sudden, all of the electrons are going to get pulled over towards this side because they see this attractive force, this positiveness over here. And because we're pulling electrons, we're creating holes. All of those holes don't want to go there. There's other holes there. They want to go to this end where they see electrons. And what we know is that we are going to go and have an equal number of electrons and holes pulled to either end of that conductor. So for a split second, when we dump this conductor inside of that field, that electrostatic field is going to go and pull electrons towards one end, push holes towards the other end. What's holding them on here? Well, it's going to be ultimately the charge separator that we have, the chemical that we have inside of that battery. Or if we take a look at, generators or transformers or anything like that, it's going to be the magnetic forces that we would have off of those. Our charge separator is what's providing all of the force at this point that is going to go, excuse me, that is going to go and hold these charges on these plates as well as hold them on either side here. If we take a look at this chunk of conductor, the very central part of our conductor over here is going to be neutral, and then we're going to just see a large chunk of negative over here and a large chunk of positive over here. Well, because it's a conductor, as soon as we would go and remove all of these forces over here, if I were to go and remove that, if I were to go and open that circuit, what would happen inside of it is instantly then I would have holes here, I'd have electrons here, and they would go and recombine. And ultimately, that's the wrong one there. And ultimately what would happen is we would go back to a balanced charge inside of that conductor at that point. What happens when we throw an insulator in between? Well, when we have an insulator in between, we are going to still have atoms, but they're stronger atoms. I hope you remember the difference between conductors, semiconductors, and insulators. Conductors, semiconductors, and insulators, as defined in first year, are going to be based upon the number of valence electrons that we are going to go and have. If we have got anywhere from 1 to 3, we can term that as being a conductor. If we have got 4, we term that as being a semiconductor. And if we have got 8, we term that, 5 to 8, we're going to go and term that as being an insulator. And we go into the theory inside of first year, and hopefully you still remember the bulk of it, but you can kind of go and, I don't know, use a cheap analogy of a gang for these ones over here. Basically, the valence electrons that are going around the outside of this one over here are going to be a small gang. They're going to be able to be bullied by outside forces. Outside forces, charge separators, are going to easily be able to go and ping, knock one of these electrons out of that valence shell and cause conduction. That's why these things are termed as being conductors, because it's easy for us to go and knock those valence electrons out. Semiconductors are kind of hard, kind of easy to knock stuff out. We do a bunch of other fancy stuff with them where we went into all that doping and trivalent and pentavalent. You covered that in your first year electronics. We'll come back into it again this year. We won't deal with those right now, but they can go either way depending on, the way that we dope them. These ones over here, 5 to 8 valence electrons, are simply going to go and be a stronger sort of gang that we are going to go and have over here, right? We've got many more electrons inside of here. Those electrons are all circling around really fast. It gets a lot harder for us to insert another electron into to bounce anything out of here, and they basically got all the rest of their forces together that are going to be, more or less ganged up against what we have for a charge separator. So it's harder for us to go and bully them out of there. They've got a stronger valence shell because they have got more of them inside of this valence shell. If we go and take a look at an insulator that has been placed now inside of an electrostatic field, that insulator is not going to break down its valence shell. Instead, what it's going to do is it's going to go and distort that valence shell. And we see that inside of here. Now they're showing these, the dielectric, which is what we call any sort of an insulator exposed to electric fields. If you got insulation, it could be, the handles of your wire strippers. As soon as you put them onto a live conductor, that is no longer termed as being insulator, it's termed as being a dielectric. It's an insulator that is going to be placed under stress, is what that actually is. These valence shells that they're showing here, they're only showing a single electron in it. In reality, we know that they're going to go and be that 5 to 8 valence electrons, but they're showing us just a single one so that we can kind of compare or understand what it is without it being too crowded of a drawing. We've got that exact same circuit that we had before. Once again, charge separator rips some electrons across to the negative side of the battery, creates holes on the other side of the battery. They don't like being crowded together inside the battery. We connect conductors and some plates up to it, and so the battery is going to expel a bunch of holes over to there. Say, get out of here, spread out, give me some room. Same with all these electrons over here are going to go and take up real estate on here. They're going to go and spread themselves out. And as a result of that, we're then going to go and have a charge that's going to be built on top of here, right? We're going to have a negative charge because we've got a bunch of negatively charged components. We're going to have a positive charge because we've got a bunch of positively charged components. And then we're going to go and take this electron, which in its normal state is going to be balanced circular. It's a poor drawing of a circle I have over here, but it is more or less circular. It should stay in a balanced state, and we are going to go and place that inside of here, and all of a sudden we've got positivity over here, and so my valence electrons, which are bound to this nucleus, they cannot escape it. They're bound to it. They're going to be like, I really just want to go over there because that looks super cool. It's a positive charge over there. And so they're going to go and distort like this, but then whoop, they get pulled back in by the nucleus. And the nucleus, in the same way, it's got a positive charge, is going to see all these negative charges over here and be like, yeah, that's kind of a cool spot over there. I'm going to try moving that way. And so what we get is we get this movement where my nucleus moves one way and my valence shell distorts the other way. And we get this distortion of the valence shell. Anytime that we've got a distorted shell, we are going to go and have forces that are going to be created. It is an elastic thing, this valence shell, and it wants, like nature always tends to want to go and balance. It wants to go back to that state over there. Right now, we're stretching it out because this charge separator has separated some electrons. These electrons have now gone to create this negative pole and stretched it over. Same with these ones here, have gone and stretched that one over. This is going to go and increase or decrease based upon the amount of electric force. If I have got a DC supply that's variable, and if I could somehow increase, the amount of voltage that I'm going to have, I would have more electrons separated, I would have more negative charge, and I would go and pull these protons further over towards this side, the nucleus, and I would have more holes as well on this side, which would pull these over. And so what I'll get is as my value of voltage changes, for the big value of voltage, I'm just trying to decide where I want to draw. For a big value of voltage, I'm going to have something that's going to look like that. For a small value of voltage, I might have something that's barely ovals like that. The bigger the amount of voltage, the more it's going to stretch. Eventually, if I go to too high of a value of voltage, I can get to the point where, like any rubber band, it breaks. I'll snap that thing. This is going to be referred to as the breakdown of the dielectric. Anytime that we take our dielectric, we stretch the rubber band so far that it snaps, and then this electron is free to go and move. That's when we have exceeded what's referred to as the dielectric strength. We've just turned it into a conductor. It's a conductor made up of what we would call insulating materials, but it is still a conductor. Any type of electron, even the ones with 5 to 8 valence electrons, or sorry, any type of atom, even the ones with 5 to 8 valence electrons, can be turned into a conductor if we get it to a high enough value of voltage. It's just really hard for us to go and do that with most of these components. But we can do it if we get to high enough value of voltage, which would be breaking down its dielectric strength. As long as we operate below the dielectric strength, we should be able to achieve this. And we want to achieve this because this is what our capacitor itself is going to go and be. All right, let's move on into our next learning task and examine how these concepts that we have, this electrostatic field, now forms a capacitor.